Greetings and welcome, friends. We've been talking about the ambiguous case of the law of sines, and I'm taking a look at our quest on page 324, and problem 13 here. It says, determine the number of possible solutions for each triangle. So I'm not solving this, I'm just figuring out how many possible triangles could there be. So the first thing I'm going to do is draw angle B, which is like a 61-degree angle. I'm guessing something like that. All right, is 61 degrees, my angle B. So side B is going to be the one that's swinging, right? My little door-hinged one. And side A is going to be my adjacent. And the question for us, all right, so first of all, we're in an acute triangle scenario. So I'm going to try to figure out what situation we land in. Actually, you know what? I might be able to open up a quick little sketch from Sketchpad just to explain this concept even further. Here we are. This is perfect. Aha. So here's the concept that we've got. So I've got my angle, I've got the adjacent, and the question is, if this opposite side is too short, it won't form a triangle. Alright, so it's like trying to reach the other side and it fails. If it's equal to the height, it will actually form a right triangle. And if it's longer than the height, you could imagine this swinging back and forth like a pendulum, and it would hit this side in two locations. So I could either have this large and acute triangle, this outermost triangle, or I could have this darker section, this sliver, this smaller, obtuse triangle as my second possibility. Alright, so this is what occurs when we have an acute one. And actually, the other possibility is if it's too long, you can see that it actually would go into a one triangle situation again. This specifically occurs when we have, what was it going to say? When it's longer than the adjacent side, right? So when it's longer than this, you can see that one triangle would occur, because if it swings over here, it's behind my angle. Alright, so a few different possibilities can occur. So for us, what I'm going to be interested in is, well, I have to be able to compare this to the height. Now, first of all, notice it's shorter than the adjacent. Okay, so that means it's not going to be so long that there's one case. But we've got to figure out this height. And do you guys remember how we figured out the height? I believe it was the adjacent times the sine of my angle. And the reason that works, if this is my height from the angle that I'm given, the height is the opposite. This is the hypotenuse in terms of this little right triangle that I'm viewing here. So sine of 61 would equal h over 12, and solving for h, I just multiply by 12. So this is kind of your setup every time for these angle side-side situations here. So let's get h is equal to the adjacent, which is 12, times sine of 61 degrees. So h is going to approximately be 12 times sine of 61. I get 10.4, well, I'll round that up to 50. 10.50. And if this is 10.50 or 10.5, 8, notice, no matter how hard it tries, 8 is less than 10. So it can't even reach on its best day to the other side. So there is no triangle here. So no triangle formed. And kind of why that occurred is because, well, because it's acute, because A is less than the height, or sorry, 8, I'll say, is less than the 10.5. All right, where I'm comparing the opposite to the height. And just to specify this a little bit further, I did construct a little table for us, looking like this, where we were able to kind of analyze our situation. So first of all, this was an angle side-side situation, or AS dollar sign, for censorship reasons. So I knew that I'd have to, consider the law of sines. However, over here, notice it says use the next table. And what does this next table tell me? It's the AS $ test. And I knew I was in an acute triangle situation. All right. I knew my adjacent was larger than the opposite. All right. So it's either of these first three, I guess. Maybe I'll actually even just take a snapshot if it'll let me. Is it not letting me? There it goes. My button wasn't clicking. Well, this will do. Let's get my finger in it, but that's okay. I'm not that picky. So let's analyze this situation. So I knew that it was one of the first three because the adjacent was the largest dimension. All right, and that's what I had here. Now the question is, how did the opposite, the 8, compare to the height? All right, that's what we're analyzing here. I've even noticed got the formula here, adjacent times sine of the angle. And we found out that our opposite was smaller, the smallest of them. The height was the medium length, and the largest length was the adjacent. And next to this on the chart, it would say no triangle, right? Is what it would say. If it's a tie between the opposite and the height, that's when it's a 90 degree, and there's one triangle. If the height is smaller and the opposite's the medium length, that's when there's two triangles formed, which is what we're going to talk about specifically in today's lesson. All right, so let's see if I can cruise through this for problem 16. So quickly draw a sketch, 37-degree angle, maybe something like this. 37 degrees for angle B, once again, so 27 is the swinging side, and 32 is the adjacent side. Now I can notice immediately that the adjacent is longer, so therefore I could conclude that it's not that one triangle situation when this is longer than this one, right? If this is too long, there's only one way it could land. So let's find the height. So h is going to equal 32 times the sine of 37. So h is about 19.26. And because 27 is longer than 19.26, all right, it's going to be able to actually hit in multiple spots, all right, where we could have two possible triangles formed, the sliver obtuse one and the larger acute one. So two triangles formed. So it's all about that analysis. So let's look at one last question. This time they actually specify in the directions. They say find all solutions for each triangle. If no solutions exist, write none. So here we've got a 107.2 degree angle. All right, so something like that. 107.2 degrees. This is angle A. My adjacent is 17.2, right? And oh, sorry, that's my opposite. My bad, my bad. If I call this over here angle C, then 12.2 is the adjacent, and the opposite is 17.2 because it's going to be opposite angle A, of course. So this is our obtuse triangle situation. Let me see if I can quickly pull up the alternate sketch that I have for that. Here we are. Bam. And in an obtuse angle side-side situation, there was only one test to consider, which was, is the opposite longer than the adjacent? All right, so you can see that there's one triangle formed in all of these situations. But the minute it gets equal to or less than the adjacent, notice it's not able to reach back over here in time. It's like, no, I can't reach. Because it'd be like I said, go out, you know, this distance into space, and then I didn't let you have enough fuel to make your journey back, and now you're like floating adrift, and it's so sad. So that's the test. Is it longer than the adjacent? Okay, and if it is, there's one solution. If it's not, there's no solution. So is 17.2 longer than the adjacent? And it is. Man, I'm getting a little bit of lag here on my mouse. So it is longer, so there's one solution. So now we could actually find the solution. So there's one triangle. Right? So let's actually figure it out. So the first thing I could find is angle C. So I would do law of sine. Sine of C over 12.2 is going to equal sine of 107.2 degrees over 17.2. So to solve, I'd multiply both sides by 12.2. Man, this lag. Ah. So sine of C is equal to 12.2 divided by 17.2 multiplied by the sine of 107.2 degrees. So how do I solve for C here? What would I do to get C by itself? Sine inverse, both sides in their entirety. So sine inverse, sine inverse. So I'm going to get C is equal to, so I'm going to do second sine inverse of 12.2 divided by 17.2 multiplied by sine of 107.2, double close parentheses. Based off of what I get there, I find angle C is equal to 42.65 degrees. So if that's angle C, how do I find angle B, my unlabeled angle? Yeah, 180 minus A plus C, right? So angle B is going to equal 180 minus parentheses, second answer, plus 107.2, close parentheses, and I'd get B is equal to 30.15 degrees. And now that I know angle B, I can find side B, right? Using the law of sines once again. And since I'm looking for a side, I'm actually going to put the sides in my numerator for the law of sines. So B over sine of 30.15. And I might as well compare it to the given information to me, the A's, since that was the original set. So 17.2 divided by sine of 107.2 degrees. And to solve this, I would just multiply both sides by sine of 30, right? 0.15. And sine of 30.15, and I will get little b is approximately 17.2 times the sine of 30.15, close parentheses, divided by the sine of 107.2, close parentheses, and I get 9.04. So we found out that this was 42-ish, this was 30-ish, and this was 9.04, which I want to point out, we can kind of, using triangle inequality, figure out, let's see, the biggest side is opposite the biggest angle, the smallest side is opposite the smallest angle, and the mediumest side, like Goldilocks would prefer it, is opposite the mediumest angle, right? So not that bad, seems like we got it right. Happy times for one triangle. Today, foreshadowing today's lesson, we're going to talk specifically about what happens when we have two triangles and I want to solve for both cases. That's what we're going to be looking at today. Thanks for watching, Internet friends. Bye-bye.